Okay, so this is tutorial 6 of week 7. I'm doing the first two questions. Okay, so question 1 reads, the air pressure in a particular room varies from point to point, given by this function. Okay, so this function generates the pressure at each point. So you see, at the coordinate x, y, z, if you want to find the pressure, you use this function, okay, which reads 3x squared plus x squared z squared, okay, exponent minus 2y. So exp minus 2y is the old notation, for e to the power of negative 2y. Okay, so this is what exp stands for. It's exponent. Okay, Euler's uh the Euler function, okay, the exponential function. Okay, so question A. At the point 102, calculate the rate of change of pressure per unit distance in the direction of this vector. Okay, so in single variable calculus, rate of change per unit distance is given by dx of the function, right? So that's single variable calculus. So you see, single variable calculus means there's only one variable. See, there's only one x. But now we're dealing with multivariable calculus. See, p is a function of x, y, z. See, there are multiple variables, 1, 2, 3. So how do you find the rate of change of a function per unit distance in the direction of a vector? So generally speaking, if you want to find the rate of change of f, so rate of change of f in the direction of, let's say, the vector a, okay? So to find the rate of change of f in the direction of a, what you need to do is take nabla f dot the unit vector of a. So I'm going to represent it like this. So this is unit vector of vector a, okay, which is given by the formula. So the unit vector of a is given by the formula a divided by magnitude of a. Okay, so just take the vector itself and divide it by its own magnitude. So that's how you get the unit vector of a specific vector. Okay, so what's the logic behind this? The logic behind this is, okay, so remember in the last class, we defined nabla to be a column vector or any vector containing partial derivatives in each direction. So partial derivative x, partial derivative y, then partial derivative z in the x, y, z entries respectively. Okay. Later on, I'm going to abbreviate this, right? You see, it's very much a hassle to write this out in full. So I'm going to abbreviate. Okay, abbreviate means just make it short by writing it like this: partial x, partial y, partial z. Okay, they have the same meaning. They have the same meaning. I just make it shorter so I don't have to write so much. Okay, so this is how I'm gonna abbreviate it. Anyways, you see, nabla has the rate of change in each direction, right? In the x direction, in the y direction, in the z direction. So if we apply nabla to f, we are finding the rate of change of f in each direction. Okay, we are finding the rate of change of f in each direction. But what is the use of dotting it with the unit vector of a? Okay, so let's forget about the unit vector of a and let's just focus on two vectors, namely nabla of f, this is a vector, and a. Okay, so like I said, nabla of f gives the rate of change in three directions: x, y, and z. So this is a vector. I'm going to represent it with an arrow, this. Okay, and a is another vector. Okay, so in 3D space, you can't just say the rate of change of a function. It's better to specify a certain direction, which we use a vector. So in this question, right, we specify the rate of change of pressure in the direction of this vector. Why? Because depending on where you point in 3D space, the rate of change of the function is different, right? Let's say you're in a room. If you move across in this direction, it might not be the same as the rate of change of temperature might not be the same as moving across in this direction. Okay, so different directions have different temperature gradients. Okay, temperature gradients means how much the temperature changes per unit meter. Okay, so you can think of it like that. But in this case, we're doing pressure. Okay, it's just similar in concept. Okay, anyways, so we have the rate of change, but we also need to specify a direction. So let's say we specify it using the vector A. Okay, so what is the use of taking nabla f dot A? Okay, the dot product, okay, let me just tell you this. Dot product gives projection of nabla f on the vector A. Okay, so what does this mean? Okay, a projection means like this. The projection of a vector on another vector, okay, so let's say we're dealing with two vectors A and B, okay, A dot B. The projection of A on B, so let's say we have A, and let's say we have B. The projection of A on B is the component of A that is parallel to B. Okay, let me say that again. The projection of A on B is the component of A that is parallel to B. Okay, so any line parallel to this dotted line is parallel to B, right? So the projection of A on B would be a vector that is like this. So let me just draw a perpendicular line like that. Okay, this, sorry, let me make my pen thicker. Okay, this is too thick, right? This vector is A dot B, or more precisely, is the magnitude of A dot B. Okay, so the size of this vector, you see, this is the component of A, the component of A that is parallel to B, right? See, you notice that this arrow is parallel to B, and it comes from A. It is a component of A that is parallel to B. Okay, so this is what you call the projection of A on B. Okay, so that's what dot product gives us, the projection of a vector on another vector, meaning it's the component of the vector that is parallel to a separate vector. Okay, so nabla f is the rate of change of f. But to specify the rate of change in a certain direction, what we do is we take the projection of f on A. So let's do the projection like this. And then we only want the component of nabla f that is parallel to A, because what we want is the rate of change in this direction, right? Parallel to A. So we project f, nabla f onto A, then we take this. So this is the projection of nabla f on A. In other words, this is nabla f dot A. Okay, so that is the reason why we take the dot product. But why do we need the unit vector, right? We're not exactly, to get the rate of change of f in the direction of A, we don't take nabla f dot A. Instead, what we do is we take nabla f dot the unit vector of A. Okay, so recall that the unit vector is a vector of magnitude 1. Okay, magnitude 1 in the direction of A. So it has the same direction as A, but it's only a size of 1 unit. Okay, so let me just represent it. Let's say A is a very long vector, so its unit vector will be only 1 unit long. So this is U, A. It's only 1 unit long. So the reason why we take the unit vector, right, is to make it fair. Okay, to make it fair. Why? Because as you know, different vectors have different lengths. Okay, different vectors have different magnitudes. Suppose I have vector A, which is 10 units long. Okay, 10 units. And then vector B is 5 units long. Okay, so the projector of nabla F on A and on B will not be the same, okay? Because the magnitudes are different, right? If I have a longer vector to project on, then that projection will be longer as well, okay? So to make it fair, we turn them all into unit vectors so that they will be converted into 1 unit and 1 unit, okay? So that means the magnitude doesn't change, but the only thing that we change is the direction, right? Yeah, so this is what makes it fair, okay? So even if you didn't get all that, never mind. The main takeaway is the rate of change of f in the direction of vector A is given by nabla F dot the unit vector of A. Okay, the unit vector of A is given by this formula where you just take A and then divide it by its own magnitude. Okay, keep in mind that if A is a vector, let's say, you know, P I plus Q J plus R K, then the magnitude of A is given by Pythagoras theorem, namely P square root of P squared plus Q squared plus R squared. Okay, so this is how you find the magnitude of a vector. Okay, so let's get started. So we want to find the rate of change of P in the direction of A. Yeah, so we need to find number P dot the unit vector A. So this is a hat sign, hat. This hat refers to unit vectors, okay? So vectors of magnitude 1. Okay, so let's first find nabla P. So nabla P, replace nabla with its definition, namely partial x, partial y, partial z. Okay, so just a reminder that I'm abbreviating the partial derivatives like this. Okay, so whenever you see this, this means I'm taking partial derivatives. And then we need to just put the p at this side. Okay, so I just replace nabla with this definition. Okay, so how do we do this? We just simply take scalar multiplication. So just multiply this into the first entry, multiply this in the second entry, multiply this in the third entry. So what this actually means, right, is partial p in the x direction, partial p in the y direction, partial p in the z direction. Okay, so to find nabla p, I need to find the partial derivatives of p in each direction and then fill up this column vector. Okay, so p is given by this expression. Okay, so now we need to find each partial derivatives. Remember that just an abbreviation that I'd like to make is this is represented by px, this is represented by py, this is represented by pz. Okay, so let's find each of them. So px means I take the partial derivatives of this whole thing in the x direction. So power bring down power minus 1, power bring down power minus 1. Remember, we treat z and y as constants, so we can just leave them as they are. Okay, so that's x. Now let's do partial p, partial y. Meaning, now I differentiate this with respect to y. So remember, x is seen as a constant, so this will go away. Then x and z are constants, so we can just keep this. Then derivative of exponent, you just copy it down, multiply by the differentiation of the inside. So this is minus 2. Then p of z, now we have to differentiate this with respect to z. X is a constant, so we'll throw that away. X and y are constants, so copy this 2 down. Then power bring down power minus 1. Okay, so this is your XYZ entry. Okay, so that means we have found nabla P. So writing down my results, I have this, this, and this, okay, x squared e to the minus 2y times 2z. So this is nabla p. Okay, so now we need to find, okay, so we're already done with nabla p. Now we need to find the unit vector of A. So remember, unit vector of A is given by A, sorry, the vector A divided by its own magnitude. Okay, so the A that we're given is this. It's given in the question. And its magnitude, you just take square root of A squared plus B squared plus C squared, which is namely these three entries, which is 1, -2, and 2. Okay, so that's how I get is 1, -2, and 2. Okay, so in the bottom, this will evaluate to 3. Okay, so now we're going to split each component in the I component, the J component, and the K component. If you do that, okay, this 3 will remain for each component. So 1/3 I minus 2/3 J plus 2/3 K. Okay, so don't forget this denominator goes to each entry, the I entry, J entry, and the K entry. Okay, so we already have nabla P from earlier. We have U. Now we can plug this in. Oh, what did it say? It says at this point, right? So that means our nabla P, we need to evaluate it at, okay, so our nabla P, we need to evaluate at 1, 0, 2. So just now, take the expression that you got, this expression, and then replace the coordinates with this point. Okay, so we're going to replace x equals to this, y equals to this, z equals to this. Okay, so that replacement, this is 1, 1, times 1 times 2 times 0, 0, 0. Then this is 1, this is 2, this is 1, this is 2, this is 1, this is 2, 2, 1. Yeah, okay, so I filled it in, then you can calculate everything. Okay, if you calculate it out, it'll be 14, -8, 4. Okay, so this is the numerical value of nabla p. Okay, so we already have the numerical value of nabla p. We already have this. Now we can fill this in. Okay, so finally, the rate of change of p in the direction of A is equal to this vector that we got, dot product with the unit vector. Okay, so the unit vector, I'm going to write it as column. This one, I'm going to, instead of writing it as ijk, we're going to write it in a column vector. So just fill the entries out. 1/3, -2/3, and 2/3. Okay, then you evaluate this dot product. So remember, dot product means x times x plus y times y plus z times z. Okay, so that's how you get the dot product. You should be able to get 38.38/3. Okay, so this is how you get the answer. Let's move on to question B. At the same point, find all directions along which the rate of change of the pressure per unit distance is 0. Okay. So we want to find a, okay, find a vector such that its rate of change of p at this point is equal to 0. Right? And just now we already found this, which is this vector. Okay. So I'm gonna define this unit vector to be ABC because we don't know the entries, right? So we just represent the entries as ABC. These are unknown entries. 0. Okay? Then we do the dot product, which means the x times x plus y times y plus z times z. So 14a minus 8b plus 4c is equal to 0. Okay, so I can divide everything by 2. Divide everything by 2. Look at this. Okay, yeah. So the vector, or at least the unit vector, such that the rate of change of p is equal to 0, must have entries that satisfy this relation. Okay, and also we need to impose another constraint. Meaning to say we need to put a condition. Okay, impose another constraint means put another condition. We need to put a condition that a, b, and c cannot be 0. Okay, a, b, and c cannot be 0 because what does a vector with 0, 0, 0 mean? A vector is 0, 0, 0 means it's a zero vector. It doesn't exist. It's okay. Apparently, ABC will satisfy this equation, right? You sub in 0, 0, 0 here. It will satisfy this equation, but it's not what we want, right? So to have a non-zero vector such that the rate of change is still 0, we must satisfy this equation while maintaining that ABC cannot be 0. Okay, so we reject the zero vector solution. Yeah, so that's all you need to write. All you need to write is this. Yeah, so let me write it as a sentence so that you all can understand. The unit vector ABC such that it satisfies 7a minus 4b plus 2c equals to 0, where a, b, c cannot be 0. Okay? So any vector of this form, as long as it satisfies these two conditions, namely, it satisfies this equation, and a, b, c are not 0, the unit vector that we make up that satisfies these two conditions will have a rate of change of 0. Okay, so that's how you tackle B. Now going to C. What does C want? At the same point, find the direction along which the rate of change in the pressure is the greatest. Okay, what is the greatest rate of change in the pressure per unit distance at this point? Okay, so we need to understand how to find the rate of change. So like I said earlier, to find the rate of change of P in the direction of A, you need to take the formula nabla P dot the unit vector of A. Okay, so let's recall what's the other formula for dot product, right? This is a dot product. So let's recall that dot product of A dot B is given by magnitude of A, magnitude of B, cosine the angle that separates them, okay? The angle of separation. So using this, let us make an expression for nabla P dot unit vector of A. So this would be nabla P unit vector of A cosine theta. Okay, theta is the angle of separation. Now, let's take a look. Can we simplify anything? Do you know what is the magnitude of this? You're taking the magnitude of a unit vector. Remember, the word unit means 1. So you know that this is actually the value of 1. Okay, the unit vector of any vector has a magnitude of 1. Okay, so we can just replace it with 1, which disappears. Okay, so now another unknown we need to find is this theta. Now, what is the rate of change such that this expression is maximum? Sorry, let me phrase that question again. What is the value of theta such that this dot product is maximum? Okay, remember what I said just now? Dot product means projection, right? So this is A, and this is nabla P. Okay, so you see, this is theta. Let's decrease the angle of separation and see visually what happens. So this will form a circle, okay? Because it's like a hand of a clock. I'm just rotating it like that, okay? It's like a hand of a clock. I'm just rotating it. So what will happen? See, what is the projection right now? The projection will be this. Okay, so now let's decrease theta. Okay, so now the projection will be this long. Okay, at first the projection is this long. Now the projection is this long. Now let's rotate it some more. Okay, and then project it like that, parallel to A. Okay. So what am I doing? So we have number P and A separated by an angle, theta. Okay. As I decrease theta, do you notice that the projection gets longer and longer? You see? Let me clean this up. Okay. At first, theta was this widest angle. Okay, and then the projection was this long. Then next, theta makes this arrow, right? Then the projection became this long. It became longer, right? Okay, let's go to the third value of theta. So the third value of theta, now the projection is this long. Do you see? The projection gets longer and longer and longer as I decrease theta. Okay, and then what is the smallest value of theta that can occur? Is when theta is equal to 0. So when theta equals to 0, nabla of P perfectly aligns with A. Okay, so that means nabla of P is parallel to A. Nabla of P is parallel to A. So only when two vectors are parallel, right, the dot product will be the maximum. And when they're parallel, theta will be equal to 0. Okay, so that's the logic behind how to get the maximum dot product. Okay, the maximum value of the dot product, which corresponds to the maximum projection. So the maximum projection occurs when the two vectors are exactly aligned. They're exactly parallel, meaning say theta is equal to 0 degrees. So to make this expression maximum, theta must be 0. Okay. So cosine of 0 is actually 1. So you see, we have this times 1 times 1. So at the end of the day, your maximum rate of change is number p. Wait, let me read the question again. The question asks for find the direction along which the rate of change. Oh, okay, yeah. So the answer is they ask for the direction where the rate of change is largest, right? So the direction is parallel to number p. Yeah, parallel to number p. Okay, parallel to number p. Then we want to find this, the magnitude of number p, right? So very easy. We want to find the magnitude of number p at the point 102. Okay. Earlier we found this to be 14i minus 8j plus 4k. So you just simply take Pythagoras theorem, this square plus this square plus this square, and it'll become 2 root 69. So this is how you get the maximum rate of change of pressure. Okay, let us move on to question 2. Question 2. Okay. Question 2 states, find a straight line which is normal to this surface, z is equal to 1 plus 2x squared plus 3y squared at this point. Hint, find a vector which is parallel to the straight line first. Okay, so they didn't do this, but what I've done for you is I plotted out this surface. Okay, so this is a surface, meaning it's in 3D space. Okay, these are a set of points that makes up a surface in 3D space. So this is actually this. Okay, so what they want you to find is a parallel normal. Okay, normal means 90 degrees, 90 degrees to the surface at this point. So I already labeled this point here, which is I labeled as A. Okay, so this is a point 1, 2, 15. So we want a line, straight line, which is okay, normal to this means 90 degrees. I hope you can see that this is 90 degrees, 90 degrees. Normal to this surface, passing through this point. So your line will go through like this, like this. So we want to find the equation of this line. Okay, the equation of this line. So remember, equation of line takes this form. X naught, Y naught, Z naught plus T times ABC. X naught, Y naught, Z naught is a known point on the line. Do we know any point on the line? Yes, it happens to be this one, right? You see, 1, 2, 15 happens to fall on this line. Okay, because we are asked to find the line that passes through this point. Okay, so we have this, but we don't have this. Okay, what is this? This is a vector that is parallel to this line. Okay, we need a vector that is parallel to this line, so we need to find it. How? Okay, so here's how you do it. Let me now lay down the steps for you. Okay, so for a given vector, for a given equation of a surface, the first thing you need to do is bring all terms to one side. Okay, bring all terms to one side of the equation to form an equation of the form f x y z is equal to 0. Okay, the next thing you need to do is calculate nabla f x y z. Okay, so the next thing you need to do is find which gives vectors normal to the surface. Okay, next, calculate number of f at the point you want. Okay, so let me explain what I mean. First of all, you're given a vector, you're given an equation of a surface. Okay, in this question, the equation of the surface is this one. You need to bring all the terms to one side. Okay, bring all the terms to one side. So one side will be 0, and another side will be a function of x, y, z. Okay, don't worry, I will go through this and it'll be clear what this means soon. Okay, after you find that, the side which is a function, you need to take the nabla of that function. Okay, take the nabla of this function. Okay, and then it will generate out another function. Okay, this one is a vector function. A vector function. So what does this vector function give? Okay, this vector function gives a function that is normal to the surface at each point. Normal to the surface at each point. So let's go back to this surface. What will nabla f give? It will give a function, let's say at this point, it will generate a vector that's normal to here, so 90 degrees. Or at this point, it will generate a normal that is 90 degrees. Okay, 90 degrees. Or over here, it will generate a normal that is 90 degrees. Okay, I'm just taking 3 points, but it will do this at all points of the surface. Okay, it will do this at all points of the surface. Here, 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 and everywhere. Okay, nabla of f, x, y, z will generate the vectors which are normal to the surface at all points of the surface. Okay, so don't worry, I will go through what I mean later. Okay, calculate nabla f at that point you want. So remember, we want to find the vector that is perpendicular to the surface at A. Okay, perpendicular to the surface at the coordinate 1, 2, 15. So by obtaining this, we shall plug in this coordinate into here. Okay, so let's go ahead and start. So we're given the vector, sorry, we're given a surface of the equation z is equal to 1 plus 2x squared plus 3y squared. So firstly, bring all the terms to one side, right? Step 1 says, bring all the terms to one side to form this equation. So let's go ahead and do that. Okay, you see, this is in the form of f x, y, z equals to 0. See, equals to 0, okay, it's the same. And then this side is a function of x, y, and z. What does it mean to be a function of x, y, and z? That it means that you see x, y, and z appear in this expression. See, you see z, you see x, you see y. So this is a function of x, y, z. Okay, so from this, we need to obtain, the next step is to obtain nabla f. So remember, step 2 says find nabla f. So let's go ahead and do that. Nabla f, the reminder that this is our f, means that, okay, so we replace nabla with its definition. So partial x, partial y, partial z. F is basically this. So I'm just going to put f here. So how do we deal with this? We just treat it as scalar multiplication. So I apply this differentiation here, this differentiation here, this differentiation here. Okay, so again, recap, this is a short form for this. Okay, just a reminder. So let's go ahead and do that. So in the first entry, we need to partially differentiate this with respect to x. Remember, z and y are seen as constants. So we only have this, right? I'm just differentiating this only because the rest of them are constants. Differentiation of constant is 0. Next, differentiate that same expression, this expression now with respect to y. So this are constants. So we only need to differentiate this one. Power bring down, power minus 1. Next, differentiate with respect to z. So this are constants. So z differentiated will become 1. Okay? So yeah, this is how you find nabla of f. So see, this is a vector function. See? This is not a vector, like it's not 1, 2, 3. It's a vector function. How do I know it's a function? Because these are variables inside. Okay. So what does this vector function nabla of f give us? This vector, right, will calculate the vector that is normal to the surface at each point. Okay, so suppose I want the normal vector at let's just say 110, 0. Okay, so I substitute this value in, -4 times 1 minus 6 times 10, 1. This will calculate -4 minus 61. That means at the point 110, 0, I don't know where 110, 0 is. I'm just gonna just take a random point. Let's just say that this is 110, 0. Okay, so at 110, 0, this vector is 90 degrees to the surface. Okay, and the vector that we got just now was 4 minus 61. Okay, that vector 4 minus 61, okay, this one is normal to the surface at the point 110, 0. Okay, so this is what the nabla of f will calculate. So let's say this is 1, 2, 3. Okay, and I want to find the vector that's normal to the surface at 1, 2, 3. So what I do is I take my nabla f and then I plug in 1, 2, 3 into this function. This will give me a vector. That vector is this vector's expression. Okay, the normal vector to the surface given by nabla f at that point. Okay, which is useful because remember we want to find the normal vector at the point 1, 2, 15. Okay, we want to find the normal vector at this point. So we want to find this normal vector. Okay, so what we do is we take our function here and then we plug in 1, 2, 15. So nabla f at 1, 2, 15 is equal to -4, 1, 2, Okay, there's no z. There's no z that shows up, so we don't need to replace 15. So this is minus 4, 12, minus 12, and 1. Okay, so at the point 1, 2, 15, the vector minus 4, minus 12, 1 is normal to the surface. Okay? It's normal 90 degrees to the surface. So that means this ABC is actually minus 4, minus 12, 1. Okay, so this is how you do this question. So plug all the things we know into the straight line equation. So this is line tutorial.